All right, welcome back. We're on 3.1, the video B right now, the second part of this, and we're going to be kind of talking a little bit about measuring this linear association and using correlation. We did this before in Algebra 2, and we're going to talk about the association between two quantitative variables. If it's linear, we can use the correlation R to help us describe the strength and direction of that, and we've done that before. Now remember that the correlation R measures the direction and strength of the association, and it's only appropriate to use the correlation to describe if it's a linear relationship, in this case R. We'll talk about what if it's not. We'll talk about that variable. Now the correlation is always going to be between -1 and 1. Obviously, if it's strong negative, it's going to be closer to -1. If it's strong positive, it's going to be close to 1. And if it's if it's not very random, or if it's very random or not much of an association, will be close to 0. So again, that sign will tell you whether it's positive or negative association. All right, the extreme values, they only occur in the case of if it's perfect. Okay, it's rarely do you ever get a perfect -1 or 1, but it should be close, like when you start getting numbers like -0.9 and positive 0.95, stuff like that. All right, so we're talking about that, and then like I said, if there's no relationship, it'll be close to 0. All right, so those are some examples of some different correlations that you see here. This graph right here, you can kind of tell there's no association. Here it's negative, but it's kind of weak. So, we kind of say -0.3. This one is positive trend, but kind of loose about a line, so about 0.5. Whereas you can see the strength, as it gets tighter about that line, that correlation increases towards that -1 or 1. And here you can see one that's nearly perfect. I mean, almost in a straight line here. They have -0.99, really strong negative. You can see those examples there to refer back to as those correlations go. Now again, correlation does not mean that one variable causes the other to happen, and that's where people mislead you in statistics. It just means that there's a relationship, there's an association. Doesn't necessarily mean one causes the other to happen. It doesn't measure the form, and it should only be used to describe linear relationships. All right, now correlation is not a resistant measure of strength. Okay, it's not resistant, very easily influenced by outliers, as we have. So how do we do this? Suppose that we have data for X and Y for n number of individuals. Now the values for the first individual are X1 and Y1. The values for the second, they're kind of paired, X2, Y2. So the means and standard deviations of the two variables are X bar and S of X for the values, and Y bar and S sub Y of the Y values. Now the correlation R between X and Y, of course, is there. All right, so that's what it is. So how correlation behaves is more important than the details of the formula. Here's some important facts about R. The correlation. Correlation requires that both variables be quantitative. The correlation makes no distinction between explanatory or response variables, no distinction there. R does not change when we change the units of measurement, so when we transform them, it stays the same. And then the correlation has no unit of measurement, it's just a number that we use for this. So again, we've gone through this before. Don't be afraid to do the tech videos if you want to remember how to go through and compute correlation with the calculator. We can certainly do that. We'll run through that as well, but you should know how to do that already. Again, as we go into the stat mode, put them in list 1, list 2, and you should be able to do those correlations that we have, linear regression as we call it. All right, so again, this is the section summary. This is what we should be able to do when we're all done, and that ends our first section in chapter 3.1. Until next time, I am Mr. Brown.